Yeah, so thanks all for having me. So I want to talk about well, I guess it's we're very much in progress with Bhargav Bhatt, Artem Kanaev, Vadim Vologodsky, and Mingjia Zhang. Also, have received a lot of really helpful, well, in fact, very critical contributions from Vadim Vologodsky. Okay, so I guess it's mostly going to be yeah, so this is mostly going to be an introductory talk for this series of talks. So I want to start with the following. So okay, so let X be a smooth formal scheme, chaotic formal scheme uh, over the formal spectrum. So so one of the motivating. Okay, so let me start with the setting. Okay, so then associated to X, we have the natural sheaf of rings of differential operators on X. So we're going to consider the sheaf called G sub X. And so this is going to be the p-adically completed p-adically completed sheaf of crystalline differential operators on X. So and associated to this, we're going to consider the category of quasi-coherent so right, so recall so G sub X. So we were in a p-torsion free setting. So this is a subsheaf of ZP linear endomorphisms of OX structure sheaf. And it's a subsheaf which is generated by multiplication by elements of OX and by vector fields. So this is the subsheaf of subsheaf, which is P completely generated by OX, so given by multiplication and by vector fields. Derivations. And so we'll consider the category. So we're considering the category of G sub X modules. Yes.
You consider P complete?
Yeah, sorry, P completely generate. Yeah, so the P completion.
No, the quasi-coherent X modules seem to be.
Yes, thank you. Yeah, everything is P complete. Thank you. Okay, so we consider this, right, and so in particular, right, so a G sub X module, it's the same thing as a quasi-coherent sheaf on X equipped with a flat connection.
Everything is happening in the P completed crystalline site.
No, it's just a quasi-coherent sheaf on X. So everything, so X is a p-adic formal scheme. So we'll talk about what we can consider quasi-coherent sheaves on X. So everything is P complete.
Maybe I should just ask, what site are you working?
I'm just working on the Zariski site. Oh, there's no
So if X is affine, then there is no need to sheaf it.
Okay, so right, so example, and X is A1 over ZP. So then we're getting exactly, and this category is exactly P complete modules over the Weyl algebra. These modules over the Weyl algebra, which is generated by right, so that's generated by elements X and E over dx with the commutation relation that they commute their commutator. So we're just considering, so in this case, we're just considering the category of P complete modules over this ring. And well, if you think about it this way, then note in particular that this category, right? So dx modules is naturally a symmetric monoidal category. It has an OX linear tensor product. So it's a monoidal category. Via the OX linear tensor point because if we have two modules with a connection, we can form their tensor product, and that will. Okay, so this is the starting point. This example of this category of picopolyc D modules on a smooth p-adic formal scheme. Okay, so maybe a motivating question is how can we deform this category as a tensor category? So what is a way of deforming this category? And this should be a way that's natural for so the question is how can we deform the category of D modules on X as a tensor category, but in a way that's natural in X. So natural overall, smooth p-adic formal schemes. Okay, so I want to start with one. I want to give one example of what this will look like, and this is an example that's I think been studied in the literature by several authors, and so the example is this notion of QD modules. QD modules. So okay, so I'm going to start by working in the case where X is a torus. So suppose X is Gn to the n cross C. Okay, so in this case, let me define for you a deformation of the category of modules with connection on the torus. So okay, so let's consider. So we'll consider a deformation. Okay, so right, so let R be the ring of functions on X. So that's the p-completion of the Laurent polynomial ring. So ZP adjoin x1 plus or minus 1, xn plus or minus 1. So we'll consider the ring. So this is going to be a deformation in the Q direction. So we'll consider the algebra R double brackets Q minus 1, where we formally added a parameter Q, and this is going to be an algebra over the ring of series ZP double brackets Q minus 1. So consider the algebra. Okay, an observation is that as an algebra, this algebra contains a collection of commuting automorphisms. So for each I between 1 and n, we'll let gamma I be the automorphism from R to R, which is defined by the formula. Well, so it's an algebra automorphism. So I need to tell you what it does to the x variables, and the condition is that it sends xj to xj if j is not equal to I, and it sends x sub I to q times x. So this defines a collection of commuting automorphisms of this algebra. All right. So let's observe. So observation is that we can consider gamma I minus 1, and that is an endomorphism. So that is a ZP. It's not a ring endomorphism, but it's a modular endomorphism over ZP double brackets Q minus 1 of R double brackets Q minus 1. And I ran out of space, but let me continue on the next board. Hopefully this is working. Okay. So observation is that this is divisible by Q minus 1. So we can consider, sorry, let me do one thing. I think I might have messed up this. Make sure I, okay, sorry. So again, so this is divisible by Q minus 1. So we can consider the element gamma I minus 1 divided by Q minus 1. So this is divisible as a linear map. It's divisible by Q minus 1. So we can consider this quotient again in the collection of all endomorphisms. so this defines such an endomorphism, and an observation is that when you set Q, when you specialize to Q equals 1, you get exactly a derivation. You get the derivation of xi times d over dxi. So note, so I don't know what to call this. What should we call this? T sub. So observe that T sub I maps to xi times d over xi. And now this is a ZP linear endomorphism of R when Q goes to 1. Because so this gives some operator, this gives some linear operator, which well, when you set Q equals 1 gives you a vector field. All right, so let's make the following definition. All right, so D sub R Q, not sure if this is the notation I should use. This is going to be the ring of Q differential operators. So this is going to be the P comma Q minus 1 complete subalgebra of, again, of this ring. So it's a P complete subalgebra of endomorphisms of R double brackets Q minus 1 is generated, well, first of all, by R double brackets Q minus 1, and also by these quantities, by these T. So this is something. So we take the subring of all endomorphisms, which is generated by these sorts of Q analogs of this vector field, and so we take the subring generated by those, and by so this will give a ring such that when you set Q equals 1, you get the ring of differential operators. Okay, so this gives the ring differential operators when Q equals. So the example that we want to consider is the category of P comma Q minus 1 adequately complete modules over this ring. So the example, I guess we'll probably come back to maybe in a later lecture, is the category of P comma Q minus 1 complete modules over this ring, P of R comma Q. So this is what I mean by an example of a deformation of the category of D modules. So maybe one thing I should explain is why this is a tensor category. So why is this naturally a tensor category? Well, you can sort of say what a module over is. So what is a module over this ring? Well, let me say, let's first say what a module over this ring is if everything is torsion free. So given a flat R double brackets Q minus 1 module, so given a flat R double brackets minus module M, well, to endow M with this structure of this larger ring of operators, which is some sort of well, I think it's called a Q connection in the literature. So to give M, right? So to give M a D R comma Q module structure. Well, it's the same thing as giving identifications. It's the same thing as giving identifications of M with its twists under these automorphisms. So it's the same thing as saying that well, it's the same thing as giving a collection of commuting automorphisms of M, which are semi-linear with respect to these automorphisms, and each of which is congruent to what the identity modulo Q minus 1. So this is equivalent to giving collection of commuting automorphisms. Right, so commuting automorphisms, or let's say commuting isomorphisms from gamma I star M. So M is a module over R double brackets Q minus 1. R double brackets Q minus 1 has these commuting automorphisms. And well, you need to give these isomorphisms like this, and they need to be congruent to the identity. When you specialize to Q equals 1, you should get the identity. So specializing to the identity. So in particular, this naturally is something that has a tensor structure. Giving these kinds of isomorphisms, I should say these are isomorphisms of R double brackets Q minus 1 modules. So it's kind of like this. You have to give isomorphisms. You get these isomorphisms which reduce the identity when you set Q equals 1. Okay, so in particular, right, so why is this a tensor category? Right, so this is why it's a tensor category, but I should say that it's a tensor category. The tensor product is the R double brackets Q minus 1 linear tensor. Okay.
So everything happens in the PQ minus 1 completed sense.
Everything is P comma Q minus 1. Okay. Right. So maybe so one comment here is that so this is in some sense this is a description. So this notion well it depended. It wasn't a definition that was made for an arbitrary R, but specifically for the torus, because we used this family of automorphisms. So this construction really depended. So this construction over here, this construction of the definition of the category of D modules depended on the choice of coordinates. And so a remark is that, here. So a remark is that so this can be done more generally. So a similar construction of the ring of Q differential operators can be carried out for any X with an Étale map from X to a torus. And the reason is that Étaleness implies that the automorphisms over here, when you base change to the Q line, deform uniquely to automorphisms of X when you base change to the Q line. So if you have Étale coordinates, you can carry out the same construction of Q differential operators. So I guess
sorry. So you explained why the tensor product is actually assuming they are torsion free. Otherwise,
assuming they're torsion.
Otherwise, it's still doable and not mysterious, but requires some.
Well, I think in general you could resolve it. You could resolve every object using torsion-free objects because the free modules are torsion. So then I think that will force the tensor product in general.
Yes, or you can write. So anyway, it's an axis. And then again, and not so. At some point, there will be something surprising. So far, everything is essentially classical. It's a variation of the themes from usual calculus. And this remark is also very much in the spirit of.
Yeah, so in fact, I guess part of the statement, and I think this and very similar statements have been explored by several other authors, is that that this construction is really independent of the coordinate. This construction of the category is really independent of the coordinate choice.
And this is already surprised.
But when P is greater than 2. sorry, so let me just say, so what we
I
show.
think it was conjectured by Scholz at some point, and then
Yeah, so I think the statement is that when P is greater than 2, that I will explain a little bit later, this construction in terms of P modules is exactly quasi-co of a stack that, well, this sort of shared version of the Q to ROM stack. So this is part of what we want to explain, whereas where this is defined without any choice of coordinates. So I think I should say this idea that this theory of PQ minus 1 complete D modules is independent of coordinates. I think it appears in an article by Scholz and so essentially the theory of prismatic cohomology will prove this if you add a further nilpotent condition.
So this article by Scholz was written slightly before before the famous article by Bhatt. Scholz introduced prismatic cohomology. And this was one of the motivations. And this is already surprising, unlike what we said before, this is a surprising result. And your story, and this is this a kind of shear? So did the word sheared already appear?
Yeah, so the word sheared already appeared because well, if you take this full category of D modules, it will naturally appear as quasi-co of the sheared to ROM stack. And so there was already, right, so the construction of the Q to ROM stack, where you would get a subcategory given by where there's an additional nilpotence condition. So maybe we'll come to say more about this later.
Yes. So anyway, the remarkable result is that if P is greater than 2, then this category is independent of coordinates in some sense. Is this condition that P is greater than 2 essential? Yes.
It's essential to our construction. So I should say that, right, so I should say that in terms of attribution, I should say that very similar results have been studied by other authors. Maybe we can say more about the details in a later talk. But maybe just to answer your question real quick, I think when we define this stack, we'll need P greater than 2, or we'll need to add a square root of Q.
But if P equals 2, then is it unknown whether this category is in some sense independent?
So as far as I understand, that there is a proof of this fact in a preprint by Chaz Matthew too. I'm not sure if it's the name correct. That is in a different flavor.
So there is. Are you saying that there is another proof which shows that P is that the case P equals 2 is not exception,
Sure. He also assumes that P is greater than 2.
Okay.
Okay, maybe we can discuss
maybe
this
a more serious question is the following. The good news is that Bart Scholz developed a certain theory, and then you are developing new theory, and these theories immediately show and conceptually show that this category is independent of coordinates. But here's a question. Suppose you want to teach calculus. The question is there a constructive version of this theory which tells you how to do the change of variables?
I'm not sure. I'm not sure I have a good answer.
So, is there anybody who is able to teach prismatic, sheared prismatic calculus?
Well,
for future medical doctors.
I think maybe Bhargav Bhatt is someone who thought a lot about this independence of coordinates in the context of the Q-Duram complex, which is
Yes, this question already appeared in connection with the Q-Duram complex, and I vaguely remember that somebody told me that A told me that B knows the answer, and it will, the proof, the details will appear shortly, but then I'm not sure whether.
I believe that there's something one can say based on that you can compare this. You can write down something explicit if you have an embedding of X in a delta scheme, and then show that any two embeddings are independent. I believe that is related to the kind of thing that
Yes.
they provide.
Yes, but in principle, it would be nice to eventually understand how to teach this to future medical doctors.
Maybe another, a remark is that there is a similar picture for the discovered by Grothendieck. He discovered that when P is 2, the category of P-complete D modules on X depends only on the reduction of X mod P. But in this case, the answer to Volodya's question is the following. It amounts to the following concrete statement that if you have an automorphism of X, which is identity mod P, then the induced automorphism of the algebra of differential operators is inner. And you can write down explicitly the P-complete differential operator, whose conjugation by which gives you this.
Can you say again what was Grothendieck's statement? He
That
said
if P is greater than 2, then the category of P-complete dx modules depends only on the reduction of X mod P only. When P is 2, it's not true.
But this is a statement about usual dx modules, not.
So maybe let me just say, right? So the motivation, right? So I mentioned this question of how one can consider deformations category of D modules, right? So I should say that in particular, the motivation is that well, one piece of motivation for this comes from the fact that D modules are a category of coefficients for de Rham cohomology, and that endomorphisms in D modules of OX is the de Rham complex, so P-complete de Rham complex, and in particular the theory, the notion of de Rham cohomology, well, has been very there are various deformations. The theory of prismatic cohomology very successfully studied deformations of de Rham cohomology, and in particular one of the ways of approaching something. Complex, and the theory of prismatic cohomology provides gives deformations of de Rham cohomology. So in particular, in this case, there's the notion of the Q de Rham complex or Q de Rham cohomology, which gives a deformation of the de Rham complex. And so one could naturally ask how to deform, well, okay, so we said that the D modules are some sort of category of coefficients. And so you could ask how to deform this category of coefficients as well. So, so in the approach, in the approach to prismatic cohomology developed in the work of Drinfeld and Bhatt-Lurie, there's a notion of prismatization, where in particular you deform the category of D modules where the P curvature is locally nilpotent. So the theory of prismatization. So this, I guess, evolved over several years, starting with the notion of the cohomology itself and deforming the de Rham cohomology or the de Rham complex. And then later there was a theory of prismatization, which gives stacky way. Well, we have sort of a geometric or stacky way of approaching prismatic cohomology, and in particular it gives a deformation, various deformations of the category, not of all D modules, but of D modules whose P curvature is locally nilpotent. So part of the motivation is whether, or the question, or a question here is whether, to what extent one can deform the full category of D modules in a similar way. Okay, so what I wanted to say about motivation.
Yeah, but my understanding is that you will not rely, you will not assume that people are familiar with usual.
Yeah, so I will try to structure this. I think we will try to structure our talks, not assuming that everyone has, not assuming familiarity with the existing theory. So Vadim gave a talk on a project when it was in an earlier stage in the fall. I'll try to avoid too much overlap, but talk. Okay, so if there are any other questions, comments. Okay, so let's start. Okay, so first let me say some conventions. Right, so maybe I should also say that, so the idea is that, well, we'll think about D modules as quasi-coherent sheaves on a stack, and then the idea will be to deform the stack. So D modules, the idea for this deformation is that D modules are quasi-co of the stack, which is the shear Jerome stack, and well, we'll deform the shear Jerome stack. Study conditions. Okay, so first I want to say something about conventions. So a stack will be a functor from P nilpotent rings points, which is a sheaf for the flat topology.
Flat means FPQC.
I think flat will mean FPQC. Yes. A stack, so we'll consider stacks in this generality, and given a stack X, we'll write quasi-co of X to be the inverse limit of the derived categories. Inverse limit of D of R whenever we have an R point of X. Not from small. So in particular, will mean that any scheme, but also any in scheme, defines a stack. Okay. And also we'll need to talk about quotients, which will be quotients with respect to the flat. So, okay. All right. That's all, I guess all I want to say about conventions. So now let me recall the following definition. So I'm going to write GH to be the group scheme, which is the divided power neighborhood of 0 inside GN. So this is the spec of everything over ZP. Adjoin then you add x to the I factorial for all I greater than. So we'll write GA sharp to be the group scheme to be the divided power neighborhood of GA at 0. Well, maybe I should say SPA, sorry. Just to be consistent, let me say SPA, because everything is going to be P. So all is everything is P. So this is, well, this is an affine formal scheme. So in particular, it defines a stack. So we'll need to consider the following variant. So GA sharp hat will be the following subfunctor of this, which will be an inch scheme. And so it'll be the co-limit as n goes to infinity of, well, of the same thing, but at the end stage, you mod out by all the monomials of degrees at least n. So it's this buff, CP adjoin I over I factorial, and you mod out by ideal generated by x to the j over j factorial for all j. Okay, so in other words, we're modding out by, well, if you think of this as a graded Hopf algebra, we're taking the quotient by by the ideal of elements of sufficiently high degree for any n, and then taking the colimit over n. So
probably you have a graded ring.
yes.
So become, of course, everything is become. Let's disregard this for a while. So the essential thing is that you have a graded ring, which is x has degree 1, and then if you a non-negative graded, and then if you first consider you can complete it with respect to the grading.
Exactly.
This is one way to say it, and then consider the formal spectrum of this topology. Or you can say that equivalently, you can say that you first take your graded ring, you pass to the quotient by the ideal of all the elements greater than something, some n. Then you consider the spectrum of this quotient, and then you consider the colimit as n goes. So you apply this general procedure to this particular case.
Yeah, so let me just write that on the board. So since we'll use this another setting in a moment. So okay, so more generally, if M is an affine scheme, with a such that the ring of functions on it has a non-negative grading. So it's the same thing as an action with the multiplicative monoid on it. With so a non-negative grading. On the ring of functions on M, then you can define a subfunctor M hat of M. And so by definition, it's going to be the colimit. Well, for each n, you take the ideal of all of everything in degree at least n, and that will define a subscheme of n, and then you take the colimit of those. So this is those. So m hat of R is going to be those R points of m, which have the property when you pull back from functions on M to R, so you're going to map of rings like this, that this annihilates everything in high enough degree. So this is a construction we can do, and if M has a group structure, this is compatible with product. So if M is a group, such that the group structure is compatible with the action of the multiplicative group, then M hat becomes a. So that's exactly what we're doing here, where we have a grading where this is integrated. All right, so this is an in scheme. So this is a subfunctor of here. So this is naturally an in scheme. And so in particular, this is an example of a group in scheme. So it's an in scheme with a group structure in the category of schemes. Group scheme. Okay, so sort of informally, if GA sharp is representing elements with the choice of divided powers, this is representing elements with the choice of nilpotent divided powers. So maybe just for now, would be a side remark is that because this kind of object seems to be relevant in general, is that okay, side remark. So GA sharp is a group in scheme, and it has a property that as an in scheme, okay, so as an in scheme, it's a sequential complement of finite schemes. So okay, so this is over subscheme. So as an in scheme, it's a sequential complement of finite schemes. Okay, so A sub n, where you could think of A sub n as everything in degree, it's a quotient by everything in degree greater than or equal to n.
It's finite scheme in finite form scheme.
Sorry, finite as so it's a finite module of A sub n is a finite module.
You have scheme, but you have spef. So
Oh, okay, finite. Well, it's a relatively, well, I should say it's relatively scheme over spef scheme. Okay, so it's a sequential complement of finite schemes over finite schemes over spef CP. And well, in this case, the A sub n's are actually finite flat over CP.
you consider this finite periodic formula schemes, right? Or you want also to take quotient by some power of p.
Okay, maybe I should just say, so okay, let's just say to make it consistent, let's say mod p to the n. So over spec z mod p to the n for any n. So then if we so then this is an in scheme over spec of z mod p to the n, and as an in scheme, it's a quotient of finite, well, of the spectra of finite algebras. Finite z mod p to the n algebras. And each of these are, in this case, in fact, these are finite flat. These individual terms are even finite flat as schemes. So I wanted to, so maybe we'll come back to this in a later lecture, but I think in this context, that means that there's some sort of notion of Cartier duality. There's some sort of notion of Cartier duality. Well, okay, so maybe in part this is a question. To what extent is there a good notion of Cartier duality between group in schemes and group schemes? But so it's reasonable to say, so well, by some reasonable definition, the Cartier dual of GA sharp hat. So when you form a Cartier dual, you should take the linear dual of functions on it. And the idea is that should just be spec of the complement of the linear duals of A sub n's. And this is in fact a group scheme. Well, in fact, it's just GA. So I just wanted to make this comment to say that in some sense, GA sharp hat is a Cartier dual to GA. I'm not sure exactly what sort of context for Cartier duality to use here, but in this case in particular, if you think of the ring of functions on GA sharp hat, it's coming from a pro-system of rings, each of which is finite and flat over, let's say, z mod p to the n for any n. So that seems like so that's something that you could just linearly dualize and take the colimit.
Yeah, so I think you are saying that you don't know the good reference for Cartier. So of course there is for commutative for schemes over a field, there is a standard notion of Cartier duality between commutative groups, schemes and commutative group in schemes. But suppose we're not over a scheme, but for instance, over Z mod P to the n, so over a channel. Then one would like to have a reference to some SGA.
Yes.
For instance, to SGA3. And I think you are saying that you don't know such a reference to
Yeah.
To standard texts, and probably we would all be grateful if somebody finds a reference
Sure.
and tells us to.
So I was just gonna, okay, so maybe part of the reason in mentioning this, which we might come back to in a future talk if there's interest, is that we'll need to consider sort of similar settings in other situations. But in other situations, we won't quite have this kind of strong statement that the individual's A sub n's are finite flat, but rather that the A sub n's as a prosystem are finite flat in some sense. And I think that's a kind of setting in which I believe one still can try to formulate, well, at least in some naive sense, a notion of Cartier duality. And okay, well, anyway, maybe the main point I wanted to make is that the GA sharp hat is well, by any definition, should be the Cartier dual of GA.
Why you see that this is should be? So I think there is a mathematical state. Either like so.
I think there is
we have a functor from rings to groups, opposite from from rings to groups. We can ask what the inner form to GM is.
Yes.
And so you are saying that in this case it's representable by G.
Yes. So I think, okay, so Vadim is saying that, right, so this is a precise sense in that both of these, there's a natural pairing from, GA, a pairing from GA and GA sharp hat into GM. And what is the pairing? Well, you can multiply two elements and then take their exponential. And I think this exhibits GA as internal Hom into GM and so forth.
Yeah, so in this context, everything is clear even without reference to GA. But you are thinking about a certain more general context where you have some questions.
Yes.
And maybe you will explain
the
questions to me privately and maybe later necessary.
Sure. All right, so let me continue. Okay, so what we wanted to explain was that so composition is that we have a natural equivalence. So in particular, GA sharp hat is a group in scheme, and it has a map to GA of groups, and we can form the quotient. We can form the quotient in this category of stacks. And the statement is that quasi-coeval is the same as, okay, so it's a derived category of D modules. So if you form this quotient, it's a well, the category of quasi-coefficient is D modules 1, and so this is, I think, sort of a version of of a result that, well, in general, in the crystalline theory, that on the crystalline theory you can describe D modules as crystals on the nilpotent crystalline site. So the nilpotent crystalline site where you require look at divided power extensions, divided power thickenings where the divided powers are nilpotent. So this is an analog of D modules on crystals on the nilpotent crystalline site.
I see. So if you remove the hat, you precisely get the ones which are p nilpotent. Sorry, nilpotent.
So there's also a version of this, which is that if you remove the hat here, if you take GA mod GA sharp, you will get not all D modules, but you will get D modules with no potent B curvature. And so maybe a related fact is that quasi-co, well, in fact, from which you can deduce this, is that quasi-co of BGA sharp hat is just modules with an endomorphism. Derived category of. Well, I guess everything is P complete. So this is again a version of this sort of Cartier duality that GA and GA sharp hat are Cartier dual. So representations of GA sharp hat are sheaves, are just quasi-co of GA. And again, this statement, if you remove the hat here, you would be getting modules where X is locally nilpotent. Okay, so this is the case of A1. What I want to say is that right, so one can do this. One can do this more generally for any smooth p-adic formal scheme. So for any smooth p-adic formal scheme, X over spot CP. So we can define the shear Durand stack of X. And so one way of expressing this is following the.
So you formulated the proposition, and then are you going to prove it now or later? So what is?
I was not planning to prove it. But maybe one thing to say is that, so I should say, so a similar statement in characteristic 0 is in the paper by Gates, Gorey, and Rosenblum. I guess in the text, crystals and D modules. And my strategy was to adapt that argument. So I'm sure we could talk more about it if you were.
So you are saying that the statement is true and proved by adapting their.
Yes. So, right, so actually we were going through this over the weekend. I think that this kind of strategy in particular involves going through INDCO. So the strategy involves going through INDCO and using some of the functoriality of INDCO. And so maybe there's a way of doing this purely within quasi-co. And one of the things that's one of the things that's maybe a little bit tricky about this was that so what is quasi-co of BGA sharp hat? Well, it's a limit of quasi-co of various in schemes. And well, maybe quasi-co of in schemes is I'm not sure how well behaved that is, but so in their work, Gates-Gorey and Rosenblum study INDCO for in schemes, and I think one can more or less adapt their arguments quite directly. But
okay. It's the statement. So anyway, we have to believe this. It's generally speaking, such statements are believable based on. It's of course it's believable because it's a paraphrase of. The classical, there is a very classical intuition about an integral connection is same of identifying fibers for infinitely close. It is based on this intuition, one would believe in this type of thing. But this is not enough to give a rigorous proof. But you are not going to discuss the proof now.
Well, I can say something.
It's better not to discuss the proof right now. Then I just asked you about this simply formulating the proposition. I wanted to know whether proof will follow or whether we just have to believe it. Now you are saying that there is a generalization of any smooth X.
So this is right. So for any smooth X, there's a shear Durham stack. Okay, so maybe I should call this the definition. Right. So for any smooth p-adic formal scheme, there's a shear Durham stack, and this is so following. Well, it's defined, and so again, this is from p-nilpotent rings to points. It's given by the formula. So as in theory of prismatization, it's the idea is that you take X and you apply it to a one truncated animated ring. Namely, it's the it's the one truncated animated ring, which is given by GA Durham applied to R. So maybe more precisely, okay, so this is X applied to, okay, so maybe I should say one more thing. So remark is that we can consider, so we can form a two-term commutative differential rated algebra, namely GA sharp. GA is a quasi-ideal. So this is a quasi-ideal. And another way of saying this is that you have this map, you have a natural map, which is for members X, and well, it's a one truncated commutative differential rated algebra. So i.e., this is a CDGA, where, well, you can multiply, this is naturally a GA module, and okay, so this is a CDGA, so it defines a one truncated animated ring. And the strategy, or the definition, is that you apply X to this one truncated animated ring. So maybe what I should have said is that so we considered this stack GA mod GA sharp hat, and this is a stack. Well, it was a stack from rings. It was a functor from p-nilpotent rings to groupoids. But in fact, it lifts to the category because GA sharp hat is a quasi-ideal. It lifts to the category of one truncated animated rings. So we can consider this as a one truncated animated ring and evaluate X on it.
Again, the magic the magic of modern life is that if you have a stack, probably, then which was a priori defined on usual rings, a functor from usual rings to groupoids, then you can also evaluate it on animated. So are you going to elaborate this or now or in the future?
Well, at least I was not planning to right now.
Not
Yeah,
now.
there's a request. We can
Yes.
elaborate.
Now, in this particular situation, when X is smooth, probably there is also another approach that you can a slightly less sophisticated approach. You can describe X Durham. Probably you can describe X Durham hat as a quotient of X by some in groupoid.
Sure. If X is embedded in affine space, then you will get a presentation. So if X is embedded in affine space, then what you'll get is a quotient of the sort of nilpotent PD completion of X inside affine space modulo GA sharp to the n.
Yes, and again, you are not explaining the details, but I'm saying a little bit something different and maybe more pleasant to use. Namely, since X is smooth, instead of embedding X, you don't have to embed here because X is already smooth. So you have a map for any X, even if it's not smooth. You have a map because GA maps to
Yes.
to this
Yes.
group of GA by GF sharp,
Yes.
you have a tautological map from, if you take X of GA, then you get just X. So X mapped to this gadget. And because the X is smooth, this map is nice.
Yes.
If X were not smooth, then this map is not so nice.
Yes.
But here it is nice, and so you can, this gives you a presentation of X deram hat as a quotient of X by a certain rather explicit intergroupoid acting on X.
Yes, thank you. So yeah, so let me just sort of say that. So right, so X sheared drum, it's something, right, so it has a natural map, a surjective map in the class topology from X. And so you can describe it as in terms of a groupoid, well, okay, so you can describe it as a groupoid quotient of X. And well, what is the fiber product? The fiber product will be the sort of well, it'll be X fibered over X drum X. And this right here will be, well, you take X cross X, you form the divided power neighborhood of the diagonal and take the sort of nilpotent completion of that, completion with respect to the divided powers. And well, so this is the PD completion of the diagonal. What's the right word to put here? Nilpotent PD completion?
Yeah, it's the hat.
Nilpotent PD neighborhood. Is it PD completion or PD neighborhood? Как это называется?
Sorry. The important completion of the PD neighborhood.
Okay. All right. And so then, okay.
So the statement is that this kind of neighborhood of the diagonal is a groupoid.
It's a groupoid.
And it is precisely this groupoid which appears as a fiber product, or another way, and moreover, the X deram hat probably, and moreover, X deram hat is the quotient of X by.
In particular, then the statement is that position, so quasi-co of X deram hat. Well, in particular, you have to give a quasi-coherent sheaf on X, and then you have to give descent data for this groupoid, which will be the same as giving the structure of a molecule for the ring of differential operators.
If X is not smooth, will this definition still work?
I don't think one will want to give this definition of X.
Sorry?
I don't think this will.
I'm afraid that in general, the map from X to X deram hat is not flat, or so, something like this fails. So in general, you have to you have to proceed as mentioned by you before my interruption. Maybe you have to embed X into something smooth, for instance, into an affine space, and then takes the PD neighborhood X inside this space, and then so this idea was explained. This idea goes back to Grothendieck's fundamental work in which he introduced, he sketched the construction of crystalline homology. So in some sense, the problem appears already in characteristic zero. so correct. So naively, the naive idea is to. So there is something which Simpson calls external. So naively, you would take X and consider the formal neighborhood diagonal, and then pass to some kind of quotient. But a better idea. But the problem is that this formal neighborhood is rather nasty because this is you look at the projection from this formal neighborhood X, one of the projections, and fibers jump. So a better idea is to first consider embed X into something references to the affine space, and then consider the formal neighborhood of X inside this affine space, and then pass to the quotient by the action of the power of the formal editing. This is the strategy more or less explained by Grothendieck in his fundamental work, or at least maybe he says some more sophisticated words than this naive explanation, but this is what he relates.
So I was just going to say, okay, so it is past 5:30, so probably we should take a break.
Yes, I think it's time for a break.
Okay, so after the break, I'll explain how bit vectors let you deform the Sheared Durham stack.
So I mean, very that's
So now I want to explain how one can use the bit vectors to define deformations of the Sheared Durham stack. Yes, question. Yes. Sorry. Sorry. I was saying maybe just say briefly and say more if there's later. I mean, the key thing is that if you have a quasi-coherent sheaf on this quotient, on this sort of quotient, and in particular, you could pull it back to get a quasi-coherent sheaf on GA, and then the statement is really that that's monadic. That pulling back preserves limits and is monadic, so you can describe quasi-coherent quotient as modules on A1 together with the action of some monad, and then to identify that with the ring of multi-tensor ring with the ring of differential operators. So the keyword is Barbeclarity. Okay, so I want to explain or this is working. So I want to explain how you can describe the Sheared Durham stack in terms of bit vectors. And right, so the first thing to say is that this is really it's supposed to be a variant of the following so really beautiful fact. So by Grunfeld, that if you're in the unshared setting, you can describe GA mod GA sharp. So in other words, this is giving you the version of the Durham stack where you see locally nilpotent D modules. Well, this is the same thing as the quotient of W, or well, when you write it this way, as the cone of multiplication by P from W to P. Okay, so this fact is sort of foundational to the theory of prismatization. And so what we want is a version of this for where you have a hat here, where you have the Sheared Durham stack. So this sort of bit vector, so we want a bit vector description of the Sheared Durham stack. Okay, so for this I need to start by going over some facts about the bit vectors. So okay, so in particular I need to describe a functor called W hat, some functors called W hat and Q. So definition. So for any ring R, well, first of all, we have W R to be the ring of p-typical bit vectors. So given an element, well, we defined, so on this board, we defined whenever you have an affine group scheme with an action of the multiplicative monoid, you can define a hat version of it. And well, the bit vectors is such a construction. So you can define so that means you have a subfunctor W of R sitting inside W of R.
So here you're using a certain action of the multiplicative group. So
X acts by multiplication by brackets X. And but very explicitly what this amounts to is defined. So it's a subgroup, subset, or let me just say is a subset of all vectors X equals, so any bit vector is uniquely has an expansion in the Persheba of VDI times brackets X sub I, and it's a subset such that all the xi's are nilpotent, and xi equals 0 for I sufficiently large. So we're considering bit vectors with finitely many components, and all of the components are nilpotent. Okay, so this is a special case of the definition that was okay. And the reason is that the ith bit component is a function on the bit scheme, which is of degree p to the I, which is a homogeneous element of degree p to the I.
yeah. So you're using. You said this, but you didn't write on the blackboard that you are using the action of the multiplicative. So first of all, the multiplicative group is embedded into W's cross. So you have the multiplicative group of width vectors. And the usual multiplicative group is a subgroup of Teichmüller elements. And therefore, this gives you an action of GM on W. And this action is non-negative, by which I mean that the action that the coordinate ring with vectors is non-negatively graded. And more explicitly, if you use the usual with coordinate components as coordinates, then the ith component has degree p to the power of I. Yes. And then you immediately see what completion.
Yeah.
This is, and you get this.
Yeah, so the bit scheme is a graded Hopf algebra. It's a graded.
Yeah, maybe there is something to keep in mind that there is at least that on the scheme of width vectors, there are at least two reasonable coordinate systems. There is the width coordinates, and there are Joyle's coordinates, or maybe Joyal's pronunciation, which are different. So the really invariant thing is this action of the multiplicative group, or equivalently the grading of the coordinate.
Mm-hmm. Yeah. So maybe a remark. Okay. So a remark is that if you say it this way, so another set of coordinates on the bit vectors, and one reason this is useful is that the bit vector Frobenius is very well behaved in the set of coordinates. It's the real coordinates, and so x and W of R belongs to W hat, if and only if all Joyelle coordinates are nilpotent. And all but finally many vanish. Because similarly, the Joyelle coordinates, which are the zeroth co-components of the iterates of delta, these are also homogeneous functions of degree. The ith function is of degree p to the n. So, okay. Right. So, okay. So, given a topological ring like ZP, we'll define for a topological ring. R, say an adic ring, or adic ring, sorry. I adic. I'm going to write W hat of R to be the limit of W hat of R mod I. So equivalently, that means that in the bit expansion, everything is topologically nilpotent, and then the bit coordinates or the JL coordinates are converging to 0. So a remark. So I make some remarks. So one remark is that W hat sitting inside W is so first of all, it's an end scheme. So as a filter, W is an affine scheme, and W hat is an end scheme. In fact, it's similar, it's an end finite scheme. So you can think of W hat as another example of such a group end scheme. Okay. The other thing to say is it's stable under Frobenius and Verschiebung. And this also follows because if you think about it, I mean, it's really just defined in terms of the grading or the GM action. And F and V don't preserve the grading, but they rescale the grading either by P or 1 over P. And in fact, this construction of M goes to M hat doesn't really depend on the grading. It depends on the grading up to any rescaling. So that means that it's stable under Frobenius and Verschiebung. Okay, so I should mention a couple of examples of this. Okay, so an example is that for P greater than 2, the element P minus Verschiebung 1 is in W hat of P, but not for P equals 2. So when P is greater than 2, this is in W hat of ZP, but not when P is equal to 2. So a slight variant is that when P equals 2, so 2 minus Verschiebung of brackets minus 1 is in W hat of Z2. And also, well, brackets minus 1 is not, minus 1 is not in W hat, but it's also true that 2 times 1 minus bracket 1 is in W hat of Z2. Okay, so one is that these can be proved pretty directly by just by computing it, because you know the ghost coordinates, and then you can work out the bit coordinates. You can check the divisibility of the bit coordinates.
So here, these things are this beautiful elementary mathematics, and so your my understanding is that you are not going to explain the details. No, it's not. It's elementary, but it requires some thinking, as usual. No,
Well, I can say a little bit about this. I can try to explain a little bit about this.
So the question is how do you at least one of the ways to approach this is to describe what W hat in terms of ghost code.
Yes.
Maybe to describe not W hat itself, but W hat of CP, because W hat, after all,
Yes.
in scheme. But what are the CP points? Because CP is P torsion free, you can describe W of CP or W hat in terms of ghost coordinates, and then you can ask, what does it mean? How to describe the condition of being in W hat of a CP in terms of ghost code.
Yes. Thanks. So did prepare this on. So let me just say this for P greater than 2.
No, it's only if you plan to discuss.
I think. Well, I just don't want to misremember and say something wrong, but I think for P greater than 2, the statement is that so given an element X in W of CP, then X belongs to W hat of ZP. If and only if, well, you can look at the ghost components So you can embed W hat as WZP into product copies of ZPs using the ghost components. And the statement is that if you take the you take the p-adic valuation of the nth ghost component of X minus n, this goes to infinity as n goes. And I think for p equals 2, you also need it to map to something in W hat of Z mod 4. It's not true when this is some general.
Yes, for p equals 2, then it's there is only an implication, and to get a necessary sufficiently condition, you need one way to say is that you have to look at something but the image in W of Z mod 4Z, and another way is to say that you get exactly one more condition. Something has to be even. I don't remember what has to be. Okay. A certain sum. And but you have some nodes, and maybe you will make them at least a certain part of these nodes available there. Because my understanding is that in these nodes, the details are in. And I remember that I tried to reconstruct the details based on Vadim's talk in October, and I was unable to reconstruct all of them.
Let me just say this is something that's kind of, I mean, it's fun.
In one direction, this is
no, but the other direction is also sort of fun and pretty straightforward. I think basically you solve for the Vit components via the ghost components, and then just look at the p-adic value.
No, of course it's straightforward, but
then you don't have to see where p.
My concrete suggestion is that maybe you can make part of your secret node public, and at least available to the participants of the set.
Okay, so is there a question?
So just so I understand, so this W hat is also a subfunctor of the formal completion of W at the like it's the if you did the same procedure to that, you would obtain this W.
Sure. I mean, I'm thinking of it as a general construction when you have a GM non-negative equated non-negative grading. But yeah, sorry, maybe if I understand your question right. So in particular, all the bit coordinates are nilpotent. So in that sense, it's
I see. So, but the Cartier dual of W. This W hat also described.
Sorry, yes. So this W hat is Cartier dual to W. So that's another thing that maybe might not prepare today, certainly. But so W hat is an infinite, it's a group infinite scheme, and it's the Cartier dual to the Vit vectors.
I have an ePrint in the archive which is called on the Lau group scheme, and there is an appendix, I don't remember, appendix B maybe, where I discuss, I give references I discuss particularity between W and W hat. Of course, it's classical, but the problem was to find references. And I think I found. I gave these references in this appendix B, which can be read independently.
But I guess I'm just confused because I thought that the formal completion of W at the origin would be the same thing where you don't impose that xi is 0 for I sufficiently large. Just that the big coordinates are null.
Yeah, so W hat is a subfunctor of the formal completion.
I see, but I thought the Cartier dual of that formal completion was W.
don't.
I think in all the even in all texts, this definition of W hat and the Cartier duality is old. I think this appears already in the 1960s, 1970s, so on, and including this condition that almost all of them are.
I mean, I think you can also write down the pairing. Anyway, okay, I wanted to mention a couple of facts about this W hat construction. Oh, okay, so maybe I should say, right, so maybe I should say a couple of general facts about this W hat construction. Okay, so proposition. So let's say R is P nilpotent now. Okay, so then the first thing is that W hat of R, it's a subset of R. The statement is that it consists of every element in W hat is P power torsion. And then statement 2 is that, well, in general, if you have a torsion element in W, it doesn't have to be in W hat, but the product of any two torsion elements is in W hat. Product xy of any x comma y in R power torsion belongs to W. Okay. So for this, let me make the following. So there's the following lemma. So let me say something about part 1 and part 2. So lemma, if X belongs to any ring, and let's say.
So when you say that it consists,
Oh, sorry.
you are saying it's an implication in one direction.
One direction, yeah, sorry. So W of R, let me say this. W of R, W hat of R is inside the P power torsion submodule of W. And then the product of any two things here is in. Okay, so the lemma that if you have an element of any ring, and let's say that, well, first of all, it's annihilated by P to the N, and let's say X to the M equals C. So it has some bounded order of torsion and some bounded order of nilpotence. Well, then the statement is P to the A times bracket X equals 0 in W of R, where A is a function only of N and. So let me say something about torsion and limit vector. I want to say something about torsion and limit vectors. And the key observation is that if you have an element such that it's bounded, you have a bound on its torsion, and if you have a bound on its nilpotence exponent, then brackets X, you have a bound on its torsion in the vectors. And this is an elementary fact, but one way of seeing it is that if you look at the Witt components of this, well, the very high Witt components are, I mean, the ith Witt component is a degree P to the I polynomial. It's homogeneous of degree P to the I. So when I is large, it's going to be 0 because of this. And when I is small, once A is sufficiently large, it's going to be 0 because of this.
I think the important thing is that such most of these statements are easy to prove once they are formulated. This is number one. Number two, it's absolutely necessary to have some text available for everyone, at least for all participants in this. And it's, I believe it's easy to do. It's just by taking part of your secret text and make it. And then everybody can. The problem is that such things requires, although it's elementary and straightforward, but this requires thinking. And one more. Question, so is it true that W hat is an ideal in this?
Yes, W hat is
Maybe
an
you
ideal.
already said it,
I
but
don't know if I said that. Yes, it's an ideal.
yes, and it's easy.
That's not that easy. Maybe I can just say something a little bit about part one and part two, but well, basically what you observe, well, you can say exactly what it means. So using this lemma that I just formulated, which I think is classical, you can also say, it's also classical, exactly what it means for a bit vector to be torsion. So if R is a key nilpotent, then X in W of R is torsion if and only if. So if you look at the Witt components, they all have some uniform bound on their exponent of nilpotents. So the Witt components xi satisfy xi to the n equals 0 for some n.
So they are, so to say, uniformly nilpotent.
Yes, uniformly nilpotent. But note that this does not have to be in W hat because you don't require that all but finally many are 0. So being torsion is this sort of uniform nilpotence exponent, which is weaker than being in W hat. W hat is saying that all but finally many are 0. Okay, so this is something, well, for example, you can prove it for an FP algebra using that P is F times V, which is V times F. And F just raises everything to all the components to the P power. And the other thing to say is that maybe I delete it somehow. Well, okay, so if you have two torsion elements, why is their product in, so proof of two is that if you have two elements which are torsion, you want to show that their product is actually in W hat. And the idea is that, well, you'll have to consider a bunch of terms of the form V to the m times brackets x times V to the n times brackets y. And the idea is that, well, x and y have some uniform nilpotents. And the idea is that all but finitely many of these products will vanish. So if x, so okay, I don't know how much detail I should give on this argument, but so if x is a sum of v to the I sub I, y is a sum of v to the j times brackets y sub j, then you have a uniform nilpotence exponent on x sub I and y sub j, and xy is going to be a sum over all I comma j of products v to the I times brackets x sub I times v to the j times brackets y sub j. And when either y, I, or j is large, well, when you the Witt vector multiplication rules will involve either a big power of p or some raising something to a high power. And then sort of by this lemma, all but finally many of the terms will vanish. Okay. So that's a useful so we'll actually use this later, which is why I wanted to say this. So the next thing I wanted to say is about the Frobenius on W hat. So let's recall, so proposition is that, so first in the usual Witt vectors, is the Frobenius from W to W is faithfully flat. In particular, it's a surjection in sheaves, and the kernel of F is identified with GA sharp. So this is how this isomorphism between W mod P and GA mod GA sharp is proved. So there's a version of this in W hat. So there's the following proposition. So one is that the Frobenius from W hat is right. So well, I'm not sure exactly. So well, let me put this way. So it is surjective in the flat topology, and in fact, as Volodia has explained to us, it's surjective in the FPPF topology. And 2 is that the kernel of F on W hat is identified with GA. So this really follows from this when you take hat everywhere. And this requires a little bit of an additional argument, but it's, well, yeah, it's maybe. Okay. Well, okay, so just, right, so I mean, how do you prove something like this? Well, any element in W hat, it's a finite sum of the things of the form like nth for Shibum, brackets y, where y is nilpotent, and then you just sort of choose enough pth roots, and then write that very explicitly as Frobenius. Maybe. So, okay, so also with this in mind, we can go.
And again, it's written in your notes, and mind it would help if you this. I would say that it would help greatly help if all the parts of your notes are relevant for this talk.
Sure. Okay, so let me just comment here that, yeah, so, right, so why, so just to go back over here, the point is that this P minus V of 1 is in the kernel of Frobenius, and the fact that it's in W hat for P greater than 2, but not for P equals 2, is just the fact that P has divided power, has no potent divided powers in ZP when P is greater than 2, but not when P is equal to 2. All right, so let me see, okay. So now let me define the construction called Q. So definition. So Q, the functor Q, is the FPQC sheaf function, FPPF of the quotient, the functor W mod W hat. Okay, so we take W quotient by this ideal W hat and then sheafify in the flat.
So it's quotient in the sense of sheaves.
In the sense of sheaf. So let me make a few comments. So the first thing to say is that it's a sheaf of delta rings. It's a sheaf of delta rings, and that's because, well, I mean, W is a sheaf of delta rings, and W hat is sort of compatible with the delta operation. Second is that, okay, so we have the Frobenius and Verschiebung on W, and they preserve W hat, so they descend to Q. So F and B descend to Q. The thing to say is that actually from P greater than 2, so now P is greater than 2, we have something nice. So FB is actually equal to BF on Q. So this is not true on the bit vectors, but it is true on Q. And what is the proof? Well, FB is P. So this is also known as P. This is also known as P, and VF is also known as B of 1. VF, by the projection formula, is multiplication by V of 1, and V of 1 is equal to P in Q when P is greater than 2, because P minus V of 1 is in W hat. So on this quotient of the bit vectors, at least when P is greater than 2, FV equals VF equals P. So when P equals 2, this is not true anymore, but there is a modification which was explained to us by Volodya. So when P is equal to 2, you can define an operator V hat from Q to Q by V hat of X equals V of brackets minus 1 times X. And
Actually, my contribution was to introduce the notation V.
well, but
Everything else was explained by well, Q and Yoko.
okay, well, so in any case, FV hat equals V hat F equals 2. So just by modifying by this unit, you can can make everything work the same. And well, that's pretty easy to deduce from over here, because 2 is equal to v of 1, but from these two facts up here. Okay. So anyway, this is just to say that for p equals 2, there is something one can.
So the nice feature of the theory is that you first learn that 2 is the number 2 is exceptional, which is pretty familiar. And then you learn that in fact, under closer consideration, it's not exceptional. It's when you slightly modify the definition. This is very refreshing.
Okay, so let me explain a couple of facts about this construction Q, which are more or less a consequence of what I already explained. But so reformulated involving Q. Okay, so Q is very helpful in setting up this construction Q is very helpful in setting up the sheared prismatization. So let me explain the following proposition. So first of all, we're going to look at multiplication by p from Q to Q. Okay, so the first thing to say is that the kernel of multiplication by p from Q to Q as a sheaf, it's isomorphic to the quotient sheaf GA sharp mod GA sharp hat. And second is that the quotient of Q mod p as a sheaf is what I'll call GA bar, which by definition is the functor that sends a p-nilpotent ring R to the colimit perfection of R mod p. Colimit perfection of R mod p. So in fact, the cone of p on Q will be relevant, and so I'm describing the kernel and the co-kernel of multiplication by p on Q as a sheaf in the fact topology.
So here, quotient is in the classical sense, not derived.
Yeah.
This is good news. And then you are saying that this is, and perfection here means colimit.
Yes. Okay, so what is the proof? Well, the idea is that okay, so P is equal to F V hat equals V F V hat F. So V hat or V is injective because a bit vector is small if and only if Verschiebung, a bit vector is in W hat is small if and only if Verschiebung of it is small.
Is what?
So a bit vector belongs to W hat if and only if Verschiebung belongs to W hat.
So this is clear from the definition.
Yes. So I forgot to say that right. So what we need is a V or V hat when P equals 2 from Q to Q is injective. That's because a bit vector belongs to W hat if and only if its Verschiebung belongs to W hat. And what is Q mod the Verschiebung? It's exactly, well, if you think of bit vectors mod the Verschiebung, mod W hat mod the Verschiebung, which is GA mod GA hat. GA mod its formal. But if you sheafify this in the flat topology, okay, sorry, maybe I said this in a slightly. Let me say this in a slightly more coherent way. So if we want to prove 2, well, we need Q mod P, which is Q mod co-kernel of P, which is the co-kernel of V hat F, because P is equal to V hat F. And now F is surjective because F is surjective on the bit vectors. So this is the co-kernel of V hat, or equivalently the co-kernel of V. But now Q mod V is, again, just by checking on pre-sheaves, is GA mod GA. And this is the same thing in the FMQC topology. The sheafification is GA bar.
Just so the problem. so your talk is a bit too condensed. And so so there are several facts here. Maybe first of all, let's consider separately the statements and the proofs. So as far as the statements, so the question is what, maybe even before considering, a general remark is that so Q, it's very important that Q is a sheafification sense. And sheafification is something not quite obvious. Yes, it takes some efforts to understand what sheafification really does.
Right. I was going to say
I'm
something.
not sure that I understand this. But another thing is that before sheafification, so what are the rules? As mentioned by Kiel, F is surjective in the sense of slang topology, both as an operator on W and as an operator on W. And this requires a little bit of thinking. On the other hand, even without thinking, it is clear that V is injective on W and on Z. And also it's injective on. Now, if you consider Q, then we have these two operators F and V, maybe F and V hat. I would say that V hat is defined for any P, but if P is greater than 2, then V hat is neutral. Now, the good news is that F and V hat commute on Q. And both products are equal to P. And this is as if you work with bit vectors in characteristic P, although there is no characteristic P assumption. So this is the first. But then we already know that F is surjective and V is injective. And now I vaguely remember that there is there is also a description of the quotient of Q, not V. But maybe there is also a description of the kernel. So one can ask, what is the co-kernel of V and Q, and one can ask what is the kernel of F. Yes, I don't know which questions have answers, but at least one can ask. But even before independently of asking what are these guys, I think there is, I vaguely remember that there is a statement, the following type of statement. Now we can consider either the ask how F acts on Q mod V, or we can ask how V acts on the kernel of F. And I vaguely remember that there are nice answers to these questions. Maybe there are isomorphisms. So you have this, we know you have the, if you wish, the cone of V. You can consider the cone of V acting and the cone of F. So because V is injective, the cone of V is concentrated to degree 0. Cone of F is concentrated degree minus. But you can also take the double. The cone, you can take the cone of F acting on the cone of V, and which is the same as the cone of phi acting on the cone of F. And maybe this double cone is zero. Maybe there, maybe F is it 2 or not? Huh?
I think it's 0.
Okay, if it's 0, so, and then this is something which can be memorized
Yeah, sorry.
regardless of the explicit description. So we have just in some crazy abelian category of, namely in the abelian category of FPP, FP sheaves, you have an object called Q. And it's equipped with operators F and V. Property that V is injective, F and V, they compute, the product equals P, and then F is surjective, V is injective, and the double cone is 0. This is one part of the story, at least as far as the confabulations are concerned. And another part of the story is that the quotient of Q mod V has an explicit, a kind of description. Actually, there are 2 descriptions. One of them is probably more or less tautological, and namely that this is a quotient of GA mod GA hat, which is, and what is GA hat? Just a formal neighborhood. So the GA as a functor, GA hat of R is the set of all nilpotence elements of. And this description of Q mod V is probably tautological if you just think about this situation. It's just a consequence of definition. But then there is another statement which says that the quotient of GA mod GA hat equals GA bar, which is defined to be the co-limit perfection of and this is requires some explanation.
Sure. Yeah, thanks. So one is right. Sorry. So I maybe I sort of garbled this a little bit. The point is this proposition is very simple, and that the point is that you want the kernel and co-kernel of P. P is either F times V hat or V hat times F. V hat is injective, F is surjective. So the kernel of multiplication by P is the kernel of F, and the co-kernel of multiplication by P is a co-kernel of V for V hat. So that's basically what goes into proving this. But then the last point is that what is the co-kernel of V hat? Well, or co-kernel of V? Well, co-kernel of V on the Witt vectors is GA. Co-kernel of V on W hat is GA hat. So you get GA mod W. And then the statement is that in the flat topology, this is the quotient as sheaves. So why is that true? Well, in the flat topology, you can make everything semi-perfect.
So for you, GA, so GA mod GA, yes, GA bar is defined to be the co-limit perfection. And now the lemma, maybe it's known to some, maybe it was known to some people, but not to me. Is that this the quotient of GA mod GA hat equals GA 5.
I could just explain that. So GA mod GA hat is isomorphic to GA bar, which is this column perfection of the mod P. And so this is on P nilpotent rings. And why is this true? Well, the first statement is that this is a sheaf because it's a colimit of, right? So I guess it's required a little bit of. The first statement is that this is actually a sheaf for the flat topology.
Just one. So GA.
Well, it's a colimit of GA.
And this is on RSP.
And so R mod P is a sheaf topology, and then taking the element along Frobenius.
And colimit just for fixed R, just colimit in the sense of presheaves. And now, if you have a sequential colimit of a sequence of sheaves, is it again a sheaf?
Yes, because this is a finite limit condition
Because
in this case.
And this is because our topology, and this is maybe it's not true for any topology, but it's true for the if so. What property of this site are we using?
We're using, I think it's like a finitary, maybe finitary is the word, that all covers are refined by finite.
Yes, because our covers are really yes, of course. Yes, and therefore we are checking commutations, and the good news is that filtered colimits commute with finite. Good.
And then the other thing is that as presheaves, these agree on rings where every element has a p through it.
So this is
So if R is a p-nilpotent ring, such that x goes to x to the p from R to R is surjective, then R modulo the nil radical is going to be a perfect ring, and it's the same as R mod p. So if you have a p-nilpotent ring, and such that any element is a p power, then when you mod out by the nil radical, it's a perfect ring. In fact, it has to be the colimit perfection.
yes. And again, it would be nice if this is made available. I remember that this part of your notes is very sketchy, and I think it uses some derived words which are not used in your current explanation. So maybe this, I think all the other parts of your talk are already doesn't require any editing, just make it public. And here, a little bit of editing. You have to edit your notes just a little, then everything will. The problem is that you're explaining a lot of things quickly, and therefore it's important for all of us to be able to.
So maybe I want to explain one important thing. So I don't know how much longer I should go today. I'm happy to keep going, but I don't know.
I'm already.
All right.
Can I
explain
even though I almost knew this.
Can I explain one important thing? So which I should have explained earlier. So this is a slightly abstract definition because it involves going through this sheafification. But in fact, there's the following statement, which was explained just by Volodya, and it's the following. So that in many cases, it really is just W mod W. So this sheafification doesn't do anything. So the position is that let R be, so let's say R is a ring, such that R mod the nil radical of R semi-normal. So this means that the equation y squared equals x cubed has only solutions of the form r squared r cubed, some r in R modulo. Notion of a semi-normal ring, which is saying that anytime you have this equation, it's sort of a this form. And so then the statement is well that Q is just the quotient of W mod W hat on R, and actually more precisely, there are no non-trivial W hat torsors on R, which implies Q of R is literally W of R on W hat. So, so this is a pretty mild condition, and another thing, which we would explain is that if in particular if R is semi-perfect, so if R mod P is semi-perfect, this applies if R mod P is semi-perfect. So a priori, this definition of Q involves the notion of W hat torsor, which could be, well, maybe very somewhat hard to control, but if you have a ring which is semi-normal, then you don't have to worry about this.
So this is the, so to say, scientific definition of, or at least one of the definitions of semi-normality, which is due to Swan in this generality. Before this, this notion was used for nice rings, let's theorem or something like this, and then semi-normality, is indeed something slightly weaker than normality. So if so a typical variety, which is so this equation y squared equals x cubed defines you a curve which is called a semi-cubic parabola or something. Yeah, the curve. So this is this curve is not normal, but it's semi-normal.
This is not semi-normal.
This is oh no, sorry. Yes, it's not so. Yeah. So what is the equation? So semi-normality means what? That if you take if you have an irreducible variety, then you can of course consider some normalization, and your original variety is obtained, so to say, by gluing something. But and then you can so the allowed things are very coarse gluing when you just take two distinct points and glue them together. But you are not allowed to glue infinitely close. This is yes. What is the exact?
Fibers are reduced. The fibers. So take normalization. Take the map from the normalization of x to x. So what is the condition? Is the condition that the fibers are reduced?
I don't remember. So just and there is also an equivalent definition of the normality, I believe, is that and maybe a more conceptual is
well, I mean, one thing to say, right? So the way that this is proved is that there's a result that semi-normality is equivalent to A1 invariance of the Picard group. The Picard group of R is the same as the Picard group of R brackets X. And then the reason for this connection is that units in R brackets X that are trivial in R are the same as the big bit vector, the hat version of the big bit vectors.
So can you write it down the last
yes,
the very last.
All right, let me just say that. Right, so the last thing to say is that, right, so H1 respect R of W hat is a subset of the kernel of pink R brackets X to pink. And for a semi-normal ring, this vanishes. So this is a statement in general, and for a semi-normal ring, this vanishes.
And maybe there is also a piece of information. So if you go to this text project and search on the word semi-normal or maybe semi-normalization, then you will find something interesting. For instance, you will find more conceptual definition of semi-normal. Yes. So I'm sorry, but
Yeah.
it's
So okay. So
yes, so we have to stop.
so
And also please make your notes available, and maybe you can do it in 2 steps. First, just make available what is the parts which require, and then maybe some other parts, for instance, story about GA. Let us thank the speaker.